Okay.
You're now embodied in the.
Yeah. Okay.
Yeah, we're all good.
We need to spend too long on this, maybe like 10 or 15 minutes. It's a relatively straightforward concept. So this is a very recent paper from Bruno's group at the Redwood Center on parameter superposition, and they're trying to solve a problem in continuous learning called catastrophic forgetting. So in general, in the continuous learning paradigm, we have multiple tasks or changing tasks. So over time, we're going to show like a batch of task 1, and then we're going to show a batch of task 2, et cetera, up to k. And what typically happens with traditional neural networks is that you do decently well on task 1, you get good accuracy, and then as soon as you start learning, starts to see a cliff of accuracy in task 2, and then it just continues to drop off catastrophically.
Is that the accuracy on? Oh, that's the accuracy on task 1.
Yeah. It would be a similar chart on average task accuracy as well, since you're essentially overweighting the recent samples. It looks like the distribution has completely shifted, and the parameters are being unlearned from the did well in the previous task. So this is a traditional problem of continuous learning.
So I think I understand this question, but let me just ask it anyway. I mean, it didn't have to be this way, right? So the assumption here is that there's some sort of like simulated annealing process going on where if you have to sort of balance out the training samples across different categories, otherwise it'll just,
yeah.
I mean, it didn't have to turn out this way.
Yeah, this is a property of traditional neural networks.
One could argue that the longer you get through all the training, then they all get trained. But in some sense, you're saying I have to train a little bit of A, then a little bit of B, then a little bit of C, and a little bit of D, and then go back to A again. And otherwise, it reaches some sort of. I mean, I understand why it does this. It's on a very high level. You might say, well, it doesn't have to be that way. Things could have been different. But anyway.
You mean the task doesn't have to be this?
The order in which you train the sample shouldn't matter, right?
Yeah, I think part of well, typically the order doesn't matter, but you train on everything at once over and over again until here you're just training on these ones. And at this point, you're not training on these anymore.
Yeah, no, but the order does matter, right? It's in some sense, I could randomize the order and it would work. Yeah, but by putting in this particular order, it doesn't work.
Yeah.
So
you could look at this as a positive property of a neural network as well. That like if the distribution fully has shifted and we're never going to see the old tasks again, why keep them around?
Yeah, right, and that's yeah, okay.
It's
So that's generally not the assumption. I mean, that's the assumption we had in our temporal memory learning. That's that you do have the more recent statistics are more meaningful. But even then, we don't have this catastrophic forgetting. We have a very slow forgetting process. So here, the general assumption under most machine learning algorithm problems, most of them, these neural network problems, but it isn't a time-based thing, and that the order doesn't reflect recency of it doesn't reflect a shift in the world statistics. So if I'm doing image classification, almost all those problems are not saying, well, more recent images matter more than the other ones. Yet the training paradigm does require that. I'm just stating the obvious from my opinion. It is a problem. It shouldn't be like.
Well, I think what they want is a line that goes like this.
Yeah.
On everything. Yeah.
This reflects like our models where really the more recency stuff is more important in that in these particular paradigms, it isn't yet it's acting as it is. So.
Yeah, there's a balance of importance of recency and just the ability to remember previous tasks at all.
There's a way that's not reflecting any factor of the world. It's an artifact. It's not the world. In our model, the world is actually changing. Here, the world is not changing. These are all equally like.
Okay. Yeah, there's no concept of continuous time here. These are
I know. It's just surprising that they have this bad property.
And there's been tons of proposals to this, which they discussed a little bit here, but they're proposing a very new solution.
So they talk about two different ways that we get task shifts. So one is that the inputs are changing distribution. So this is like from the fashion eminence data sets. These are like pants that are rotating. So you actually are rotating the images slightly over time. So you might have 0 degrees here and 2 degrees here and 4 degrees in task 3. So that's one type of task change, and the other is the change in the labels of the data set. So in the SciFAR case, you might have 10 labels from SciFAR 10, and then the next task might be another 10 labels chosen from SciFAR 100. And so they're actually it's the outputs that we're producing that are changing. So in both cases, it's a distributional shift. That's the labels are changing versus the input controls are changing. But we see this problem in continuous learning in both cases. So the general background, so the premise behind this paper is that neural networks in general are over-parameterized. So the parameter space is extremely high dimensional. But the inputs, the things we're trying to model, they sit on a low-dimensional manifold. So it's a much smaller dimensionality that sits within a larger parameter space, and that means that potentially the neural networks have this potential to pack parameters, multiple manifolds into the same large parameter space, one for each task, without any cross-influence.
So you're saying
Interference.
the possibility is to solve the problem.
Yeah, it seems theoretically possible to pack these in a better way, in a more efficient way. And so the idea that they raise in this paper is to pack these using a context matrix, essentially a transformation or rotation. So what they're going to do is they're going to choose a particular context matrix for every single task, and this is fixed. These aren't learned parameters. And we're going to use these to both store updates to the weights as well as retrieve the weights for a particular task. So when we're on task 1, we're going to have C1, and C1 is going to take every input, rotate it, and then weight updates are going to be sort of addressed into the parameter space based on this context matrix. And so we don't have to, this is given. We know that we're on task 1, so we're going to be using C1. We know that as soon as task 2 starts, we have a totally different matrix, C2. That is a different transformation.
Just the parameters of the network?
No, this is a rotation or a transformation.
But what does it actually represent? I'm sorry.
It's sort of like an address into a parameter space. That's how I've been thinking about it. So we have a huge parameter space. The context is transforming parameters or inputs into one section, one subspace of the parameter space that's going to be used just for that task. So we're trying to kind of subdivide the subspaces that the parameters sit in.
How do they? You obviously can't pack all that into a single point in the parameter space. So you have to set some sort of a cloud on the parameter space or something. Yeah.
Yes, if you think about the weight matrix is a big matrix, it represents a big space of possibilities.
Yeah.
And context one might say, for this context, you're only going to use this part of the
Yeah, but how
weight
are
matrix.
you defining that? I mean, it's not so easy to define this part.
Yeah, so they're defined based on, so you choose these context matrices as they're just transformations. So like a really simple version of this is a binary context where you take every element and you either multiply by 1 or -1, and you randomly choose where these -1s fall. And so what this is doing is it's doing like rotation on the inputs in a way that it makes the inputs, it's an orthogonal rotation. It pushes inputs into maximum by n matrix. It is addressing, as you're learning task 2, you're making updates to parts of the weight matrix that are nowhere near the parts
Particularly, you've made this point many times, that when you have a sparse activation or sparse representation, it makes it easy to do this diagonalization, right? It's natural.
I think it is harder, I think.
I think that
you have to be very careful how you choose these contexts. There's a number of different ways of choosing these context matrices that they talk about, and they have different impacts, and it's not, you have to know what the context is. You have to know which task you're in, which you don't need to necessarily for sparse representation. So I think there's definitely challenges.
I mean, it's almost like if you do this really well, it almost seems like you'll end up with something like sparse weights or something like that. It's almost inherent to the problem that if you have non-sparse weight matrix, that you're going to have these proximal overlaps that it's almost inevitable, it seems.
Yeah.
Am I right?
Yeah.
Am I correct? Interpreting that correctly?
They might not end up with sparse stuff, but they'll be kind of similar, but using these sparse because it's just some random rotation of the.
It's low dimensional manifold, but it doesn't mean that it's sparse.
Yeah.
Well, it's just that all weights can't participate equally in all tasks, right?
You might end up with sparse representations this way, actually, because if I understand it correctly, for task 1, if you're sending in inputs, some set of dot products will be positive and the values will be active. If you're in task 2, it's an orthogonal rotation of the weights, and it'll be a different set of values that's going to be activated because dot products are going to be in a different set of values. So for any given task, it might actually just end up being a small set of units that are active. Is that?
It seems possible. I mean, they don't mention that result.
Almost might be almost guaranteed to happen.
Because it's values.
Huh?
Because
the values are different. Yeah, because if you have and correct me if my interpretation is wrong on this or not, but, because each context is gonna be in the best ways, a completely orthonormal, rotation of the weight matrix. And so this set of inputs that cause the dot products to be high, it's gonna be completely different.
Yeah, I'm just not totally getting how that results in sparse activations.
Because if you have 10 tasks, then I don't know if it'll result in sparse, but I think the set of values that would be active would be quite different in each one.
Yeah, so I think maximally different is the goal.
Yeah.
But whether it's less, I'm not sure.
Yeah.
See, Disney, I don't understand your argument in terms of values. I mean, but I've come about this in a different way, so that's better or worse, but I've long struggled trying to understand the nature of high dimensional spaces. They're really, really weird, right? It's really hard to visualize and think about them, especially if they're binary or very low resolution, very high dimensionality. And so it's just always like, it felt like it was only when you actually sort of laid out the sparse argument, which of course I sort of totally knew too, but you kind of made it clear somehow, that I came to the conclusion that the only way to really think about these spaces so they don't collapse, so they don't stack these different, the only way you can even possibly get to having manifolds that don't just constantly step on each other is to just have this sparsity. It's just to reduce the dimensionality of the subspace. And so I don't know if that's right, but in the back of my mind, that's like, I've kind of accepted that as a fact. So in some sense, I'm saying if you're going to solve the problem, you're going to end up there. And so I'm testing my knowledge about it. I don't understand your regular argument. I don't get that at all. But I didn't really read the paper. So I'm just saying from a different direction, it feels like that it has to do this in the end. Somehow Haskell's manifolds have to be just really sort of separated in space, and therefore they have to be low dimensionality, therefore they have to be sparse. Does that make sense in any sense? I don't know if I'm just like dreaming or something.
Yeah, I think mathematically they don't have to be sparse. You can take any sparse,
Rotating exactly?
the entire space.
What,
So if you
space, right?
input space, yeah. So if the input space is very sparse initially, and you have these.
Right, the matrix, the connectivity, the sparse connectivity.
No, the same thing on the weight space. The weights are very sparse in our
But
models.
when I rotate the input space, I'm not necessarily rotating.
No, but you could rotate the weight space.
But it doesn't necessarily, why would it? I wouldn't expect it to. But the whole point is like, I don't really want to rotate the weight.
No, I'm just saying that the property still holds in a rotated version of that thing, and in the rotated version, you're not sparse anymore, you're dense.
So you change the reference frame by 1 degree.
Yeah,
And everything
just
was
by 1
zero,
degree.
it's not
Everything,
zero now.
exactly.
I guess I'm arguing that wouldn't happen in the weight space. That can happen, that the whole point is taking that crazy input.
No, we don't want it, we don't do that, but mathematically, it's possible, and you still get the same properties. It's just that now, instead of having 20 synapses, you have thousands of synapses on each dendrite, which we wouldn't want. But you
That's
would
the
still
property
get
of the.
and that's kind of what they're doing here, is they're.
I mean, you can get your work, but wouldn't you lose your robustness? I mean, isn't that the whole problem with these networks? I mean,
You would lose the robustness if you still use the dot product, but if you use some rotated distance metric, then it would
all right,
still work.
you're losing me.
It's kind of a.
Okay.
I'm just saying mathematically, they're all kind of the same, but in practice, I think sparse makes a lot more sense.
I had maybe
I don't know if you agree
incorrectly
with me.
gone to the conclusion that,
Okay.
I may have incorrectly reached the conclusion that the sparsity is always going to be the solution. And, because he can understand that one, but maybe I'm wrong about that.
I think it's the best solution.
Okay.
So you're telling that the subspaces, the dim of these subspaces is like very low, right? If you take for W stack, if you take its M, you're telling for these subspaces, the dim of the subspaces is
Much
very
lower than M, yeah.
Okay.
So, I mean, yeah, all of this depends upon this property of manifolds, that they're low dimensional. The input space is low dimensional. I think the sparsity might be a good heuristic for finding the manifold, but I'm not sure it's the only one, right? This is a demonstration of a non-sparse way of essentially identifying these manifolds and then rotating them away from each other.
Well, it's the only way I've learned to be able to think about the problem. So prior to that visualization, just trying to imagine, low dimensional manifolds and this how they connect to space just seems crazy. I just can't think of it. Mathematically, maybe it works. the limit of my brain.
Definitely not
So
intuitive
if
for me
the
either.
limit is low, if the limit is low, there is always like representation you can do this sparse representation. If the limit is low, I mean, compared to the original weight matrix, literally it's like the limit is like m. For the subspace, if the limit is very low, then we can always find a like sparse representation. But I'm not sure like using these rotations whether it's possible to find one.
Find a sparse representation.
Yeah.
Yeah.
But there's no
Sparse is
concept of
just
sparsity.
Yeah, it's not the,
Okay,
it's
yeah.
not the premise.
There's no.
All right. So I actually didn't get paid, so I don't know how well they've done this, but anyway.
They slightly beat state of the art. Which is, yes. I mean, I don't know, 97.6 up from 97. I think state of the art was elastic weight consolidation.
No, it's not. It was 974 and then we got 976.
Yeah.
It's kind of splitting hairs.
So that, aren't we talking about solving the catastrophic forgetting problem?
Yeah.
They solved, so they
So
solved
that
it.
should be a minor improvement, that's either catastrophic
Yeah, yeah.
or forgets or doesn't.
It's a major improvement over traditional neural
But it's
networks.
an improvement over other algorithms that solve the catastrophic forgetting problem. So it's comparing against other solutions to that problem. Not comparing against neural
I
networks.
see.
Yeah, there's like 2 or 3 other proposals to solving the catastrophic forgetting.
Is it easy to state them very simply in like one sentence?
Yeah, so one is called a replay thing, which is as you're training task 2, you also throw in a few of task 1
Well,
there.
that's, okay. well,
So that's how that works.
That's cheating.
That's
It's like, look away, I'm still training here. Okay.
That's the replay one. There's synaptic intelligence and elastic weight consolidation, I think are very similar.
What I picked up from EW's elastic weight consolidation was that you sort of keep a memory of the weights that performed well on task 1, and then you set up a loss function that tries to incentivize keeping those weights where they are. So not allowing them to be interfered with by task 2.
That's why they call it elastic, like we're always pulling.
Yeah, it's like a
weight.
string.
That's kind of a little bit like ours, in the sense that our dendritic segment is like sort of the extreme form of elasticity. Just put them all in one section over here and
Yeah.
don't touch them.
And they only get reused when you're some sort of massive capacity. That's when you start reusing them.
Yeah, exactly. I mean, I was thinking about, I didn't bring it up here, but there's this huge sort of theory about what should happen in a real world, right? In a real world, you should remember everything, but then you run out of memory, and that's when you start losing stuff. And then what do you lose? But then you start losing the things you haven't learned most recently or something like that. So that's the way the system should work. That's the way the simple memory works.
With EWC, it might be synaptic intelligence, the intuition, or once it was something like this. It was, if you imagine you're in weight space, and here's a weight. This is some very high dimensional space. Here's a weight.
Fine, it's looks like it's a dot.
Yeah, get the point? Sorry. It's a dot product.
That's a particular point.
All right, stop
Are
right
you
now.
saying, are you saying that's a particular point in the very high dimensional space?
Yes.
Okay.
The block is.
There's just 10,000 dimensional space at
Yeah.
that point.
So it's a point in a very high dimensional space, and you've trained it on task 1, right? And now you're training it on task 2, and you have a choice of how to update this weight. If you look at task 1, it may be that there's a whole bunch of directions you can move it in, which would not affect task 1's performance. And there's a whole bunch of directions you can move it in that would be beneficial for task 2. And there's this narrow range, or there is a range here that intersects where you don't affect task 1, but improve task 2. And see, that's the direction you want to go in. And if you're in a very high dimensional space, there's always these overlaps.
That's a really crappy way of doing it. I'm biased, right? Because we have a solution to this problem. But, that could be like, saying, oh, you really want to get to San Jose, but the best you can do right now is head towards Fremont. I mean, it's like, So.
Yeah, it's limiting. But I think at the end of the day, it might actually be doing something very similar to this.
Yeah.
Because when you make the updates for weight 2, you're trying to do it in a way that doesn't affect under this rotation. So I think it may actually end up being very similar.
It seems like a different strategy because this is all about just maximizing the similarities. So there's
Yeah,
very little chance of overlap. Whereas this
Right.
seems like we know they're going to be in the same space, but let's just make sure that we're updating them in a way that doesn't destroy the previous functionality.
Yeah, but the one way to not destroy it is to effectively do these
Yeah, yeah,
rotations,
yeah.
right?
I mean, I'm not even let you finish your presentation, but, you know, this is a very important question here, I think. I mean, we have to ask ourselves, in the future of AI, is it possible and to achieve all these results using point neurons, basically, and non-sparse? There's two questions, point neurons and non-sparse representation. Is it possible? Or is it impossible? We know the brain doesn't do it that way. We know the brain has an elegant solution, which is sparse representations and non-point neurons, and it's elegant and it works. So really the question is, can it be achieved this way? And if you can achieve all the same results this way, then the world is probably going to go that way. If you can't achieve the results this way, then the world's going to go the brain way. So it's worth asking these questions and try to keep them in mind. It's less about, you know, how this paper goes. I'm trying to figure out what's the ultimate disposition of these questions.
Yeah, and it's not just achieving one result, it's sort of, can you do everything that we need to do?
Yeah, I know, that's always the case, right?
Part of that, I think, is power efficiency, for example.
Yeah, all right.
And so
That may be-
it's very hard to do with that.
Maybe, you know, you have a lot of different directions you can go to convince people to do it one way or the other. Maybe that's the way to go.
Yeah, computational efficiency, sparse stuff is always going to be better, I think.
You know, in the past, I've always been dismissive of all point neuron solutions, and I've learned not to be because they've really done some very significant things. So, you know, so I'm just always a little nervous. Okay, so.
But so your general point from the biology is that we just keep on learning until we hit capacity and then we start forgetting things.
And we forget things, and then we forget things based on a set of heuristics that have to do with, in biology, it's complex. It's heuristics about how recently you reinforce that thing.
Or salient or
Yeah,
whatever.
well, recently, or some sort of major, yeah, so we model that with this permanence value, which really just reflects recency.
Yeah.
Or it reflects a combination of recency and time, number of times we had how recent. The real biology is a little more complicated than that, but yes, there's something, and so we just keep learning, and we don't really forget until we kind of max out. Now, obviously, in the brain, we actually do forget things on a regular basis, partly because it's just natural. In our models, we don't. We can just keep learning until we run out.
It seems like there's some parallels with what they're doing here. Every time a new task is coming in, we're rotating in a way that we're like packing it into our memory in a way that's going to, as little as possible, interfere with previous memories. And at some point, we're going to hit capacity, and then we're going to start doing rotations that do interfere with previous manifolds and learn knowledge. And the way that those rotations are selected,
But with this fully connected network, as Subutai was just saying, as you're trying to learn new things, you are actually affecting or you're trying to avoid affecting the, you have to run a lot of effort not to avoid your previous learning. I mean, I don't know how complex these operations are.
I think the effectiveness of this paper all boils down to how they choose these C matrices.
Yeah.
Yeah, that's the key thing.
And that was maybe my first question, like, right, where
How
does
does
it
it
come
go?
from?
Yeah.
Yeah, totally.
So they're essentially randomly chosen rotations of various forms, and there's a few that they experiment with. One of
When
them,
we say rotation, are you saying actually physical rotation or just some mathematical term that's something else?
it's like physical rotation. I mean, in 3 dimensions, it's physical
Well,
rotation. It's a
That's
matrix
assuming
can,
certain types of problems, then that's just assuming you're modeling some physical structure that can rotate, right?
No, it's a rotation of it's a mathematical
Okay,
rotation. It's rotating a vector into
Okay.
space.
yeah,
Okay.
sorry, it's not but in 3D space, it's just a rotation. So yeah, any like square matrix is a linear transformation. Some of them are considered rotation matrices. I guess a subset. But in general, these are just transformations. So yeah, we're doing some sort of warping and rotation of space to get either inputs or parameters into distant parts of the parameter space. So they sort of the rotation. The problem with this one was that this is essentially a dense rotation matrix. So every one of these values is populated, meaning that you have to add m squared parameters for every additional task you want to learn. And so this was inefficient. We were a little bit confused by why this is so problematic, since these aren't learned parameters. These are just these are like hyperparameters. They're fixed before training starts. So it still seems like this is potentially useful, but they don't really report our results from this one. They tried this complex and this binary.
actually, these are 3 things that they talked about in the paper.
Styles of producing contexts.
Okay.
Ways to produce these
Okay,
context
okay,
matrices.
okay. So they explored all 3 of these.
Yeah.
What are you talking about?
And the complex seems to perform better than the binary. The complex is tough because you're actually dealing with complex values in the matrix, and so you have to make adjustments to the way that.
They're talking about mathematical complex, like complex numbers?
Complex numbers.
What does that mean in terms of neuroscience, anything?
Neuroscience?
That's a lot. People are starting to use, I feel like phasors to describe the way that even like temporal like oscillation patterns, right? So like oscillations can be described by phasors, and so
Sure, that makes
you
sense.
can see if two oscillations are phase aligned,
Yeah.
additive impacts. I
Yeah.
think they're
I can see that. It didn't strike me as odd, but it's talking about complex operations, complex numbers.
I don't have a great intuition for this. The way it works is it's a diagonal matrix like this, and every one of the diagonal entries is a different rotation on a unit circle. And so it ends up being a big transformation
Wow.
where each entry is a single negative pi to pi rotation.
Mhm.
And then the binary version is just the same thing, whether you're sampling uniformly at random from -1 and 1. And so you just get a binary diagonal like this. And so what that means is each axis, each dimension is either flipped or not flipped. And so that ends up being an orthogonal transformation as well. That allows you to push the
Almost
parameters.
certainly, right? If you have
By
enough, if you have enough definitions, then you'll.
Yeah, even if you only flip one axis, you end up getting into a really different part of the space.
Yeah, but to be completely, or it would be nice.
I think orthogonal is still defined even if most of the dimensions are the same. I think it's still an orthogonal transformation if you only flip one, I think. I'm not positive about that.
Hmm. But if you flip them all randomly, then you'll guarantee you get it. Yeah, that's what gets really hard to think about things like the high dimensions for me. Like,
Yeah.
like, if you're trying to think of what is the orthogonal vector in a high dimensional space, it's so hard.
Oh, it's impossible, yeah.
We were trying yesterday, right? We were trying like imagine this manifold. How we were talking about like.
But it actually gets easier in very high dimensional spaces, almost any random, two
Right.
random vectors
Just
are
no
very
clear.
likely to be
Yeah.
Were they like,
close to
were
orthogonal,
they orthogonal?
or close to orthogonal, yeah, I think.
Yeah, I'm not sure. There's a great slide from Jeffrey Hinton at some point. It's like giving advice on how to think about high dimensional space. And he says, just think of it in 3-dimensional space and then tell yourself really loudly, 13, 13, 13, 13. I haven't tested that, I'm not sure if it works. Yeah, I think this is it. So they were seeing pretty good, obviously they beat the kind of state of the art with both the complex and the binary context selections. The limitations, to me, one of the big limitations, and this is outside of the scope of this paper, was that these contexts have to be predefined. In the real world, of course, we have no idea what context we're in.
Yeah.
We're not given a label of a task shift.
Mhm.
So it's nice to be able to just say, okay, now we're in task 2, now we have a completely
Oh,
different
I see.
rotation.
It basically requires completely labeled data, you're saying. Is that-
Not labeled data, but labeled tasks. So we know that we're in task 2 from task 1, and so we pick a totally
How's that different than labeled data? I mean,
Well, it depends on how
oh.
the tasks are changing. If you think about fashion eminence, where you have rotations,
Yeah.
the task shift is actually just a 2-degree rotation of the images. So there's no label change, it's just the distribution of the input that's changing.
It's still a supervised learning tool,
Oh.
at least the ones they.
Well, okay, it's a different type of label,
It's an
right?
additional.
Yeah.
I mean,
Yeah, that's right.
okay, it's a different type of label. You have to know.
It's
You
it's
have
like
to
we
that-
know the context that shifted.
Yeah.
I'm just telling you, okay, now you're in context 2, so you're gonna be rotating your.
But you even know that it's shifted 2 degrees to the right or 4 degrees to the left. It's not like,
You don't
Yeah. You just know something has changed.
oh, they
you
don't
know it's a new
tell.
context, yeah.
You could combine some sort of heuristics to detect distribution shifts and then.
Yeah, yes.
Right.
It doesn't seem like that hard of a problem to automatically detect these things, but we have no idea yet necessarily how the brain is
Wow,
detecting.
Actually, you need to know the index of the context matrix too, so you do need to know
Oh, yeah.
which.
Which
task,
context
right?
it is, yeah.
So
You just, yeah, so what I said earlier wasn't correct. It's not enough to know just that the context changed. You also need to know which one you're in.
No, you're
I
right.
mean, it's
We
good
need a
dictionary
mapping.
saying like-
Can you help me on context and index? Is context like what numeral and index is what the rotation is, or was
No, context is what task.
So the context, each of these is a context matrix, one per task.
What, again, what is a task? Just,
So this is an example here with rotating fashion eminence, where you have images that are coming in, you're
Yeah.
classifying them as like pants or shoes.
yeah, which is a task is what?
So task 1 is 0 degrees rotation, task 2 is 1 degree rotation.
0 degrees case of a particular object.
Of all of the
All
entire data
objects.
set. So it's like a full distribution.
So the task is like an operator on all objects.
Yeah,
Yeah.
well,
and-
in this case.
An easier one to think about is this, what's called incremental C from Cypher. So Cypher, you have like 10 labels of images, and then you have a totally different set of images with totally 10 new labels that you haven't seen before. So that's a much clearer task boundary, because you're trying to produce different labels, and the inputs are completely different.
But in this case, you'd have to know, okay, now I'm getting images from these 10 categories, and now I'm getting images from the second set of 10 categories, and now I'm getting images from this third set of
Yeah, maybe you use some
categories.
sort of like K-net on the color space, like what Pranala was talking
Yeah,
about, right?
So
Like
the
something, some
The
heuristic to
task
figure
is
out where we
in
are
this example is the rotation.
in that.
In
example.
that one, yeah. It's just a different, task is just a different setting that you're in. You're now learning new things that you weren't.
But they could be the
learning
same categories.
before. It could be, yeah.
That's what they are, right? It's-
Yeah.
There's two kinds. There's the label change or the inputs change. This is the inputs change.
You need to keep some sort of dictionary saying,
Yeah.
this distribution is this context, and then
Yeah.
anytime you see a distribution you already detected in the past, then you find it in the dictionary.
I always
It's
felt
a very
that,
artificial kind of
yeah,
set.
to me, this idea that you have some, it's almost like assuming some sort of physics of the world that there are these uniform operations, or I just call them tasks that can be performed. But I always felt that the best brain models wouldn't make any assumptions about the world. Yeah,
No, we don't. We have to figure out ourselves
Yeah.
how to do it.
yeah, but it's not even an underlying assumption that you just don't want to rely on some sort of knowledge like that in your algorithms.
Yeah, but implicitly we have to build context of some sort because we know that certain kinds of behaviors are going to be useful in one context and different behavior will be useful in another context. The same exact behavior is going to perform differently.
Yeah.
So we need some notion of
We
Top
need
down.
no, some notion, but we figure it out ourselves.
Yeah,
absolutely.
Yeah.
It's not given
And
from.
maybe it is not your dogma.
Yeah.
Some tasks could be more similar than others.
Yeah, for sure.
In that case,
Yeah.
they're completely yourself.
Again, I may be totally like getting beyond my ability to think here, but to me, the beauty of the grid cell thing is that it said, okay, the common functional operation that you can apply to everything is movement through grid cell space or through, and that there's this whole world of how behaviors change things in the world, and it has to fit into like these metric spaces. I don't know if that means anything, but it's like that's where the rubber hits the road in these things. That it wouldn't be, and so you wouldn't have any of these properties in the network like this. I don't know.
In the grid cell world, the context is like, what part of the space am I in, right? It's a huge space, and you're like,
I didn't know, I'm afraid to use these word context now, I'm really lost about context.
it's like hierarchy essentially.
In our temporal memory, the location SDR acts as context for the sensory layer. Right? That's for our temporal memory.
Yeah.
So
Yeah.
in our language, that works. It's not the same context.
I mean, I was thinking literally rotating these pants, right?
Yeah, maybe that's not the best one. It's from the paper. I took it from the
Yeah,
paper.
no, it's okay, it's
There,
all right, you
it's
talk
okay.
about coffee cups, they can talk about pants. I'm gonna let it pass, I don't think it's worth it.
I think there's one inefficiency here which I don't like. If you take the CIFAR, incremental CIFAR case, if you learn 10 categories of CIFAR, and now you're learning another 10 categories, you might have learned features in the first 10 that would be very useful for the second 10.
Yeah, you're right about that.
Here, they don't allow that.
Unless the contexts are smarter.
Unless the context
Yeah,
are smart.
They're
so
making
it's the
things
next step,
closer.
right?
Yeah,
The last line of the paper says they're looking into learn context. They're looking into how to use gradient descent to learn the context. That's
But that wouldn't help either, because in this case, if either you have a new context or you have the same context.
Yeah.
If you have the same context, you're gonna get forgetting. If you have a new
No, I
context,
think there's a way to do it because you're learning the context, essentially they're like vectors and you're trying to get them orthogonal initially. But now you can actually learn that actually task 1, task 2 are super similar. Let's transform them very close to each other. A little bit different, but with some overlap. Then we might be able to reuse parameters.
So they can start orthogonal and then they can move closer to each other. So if they're not orthogonal, then
without remembering and without retraining on the original set.
Yeah, this is theoretical. I don't know whether that is going to work or not, but I feel like we can speculate and say it's possible that if these parameters live near each other, that they might be able to reuse some of that.
and one thing that can happen if you do this is you can learn a task using a context, and then you can learn a completely different task, but then this context gets close together, and then you can improve on task A just by learning task B. Just you realize, if the context get together in this space.
You can even have context.
That's one thing that could happen.
You can even merge context. You can learn that actually we don't have to. Like 1 and 2 are actually from the exact same distribution, so eventually perhaps their context
So
actually
you
collapse.
can improve on task A just by training task A.
Yeah, that was outside the scope of their work here. And there's nothing to share here. This was just me trying to wrap my mind around how these transformations are working. The one thing they say in the paper is that, you know, instead of thinking about this as doing transformations on the parameter space, you can look at it as every time a training sample comes in X, you actually transform X. And it's the same because matrix multiplication is associative. So it's slightly easier to think about. Input comes in, you transform it, and then you're actually learning a single weight parameter W.
Mm-hmm.
So that's a slightly more intuitive way of thinking about the same thing that's happening.
We usually represent vectors as columns. Not rows.
Yeah.
You don't have to put extra, so it's just a column. So
You don't have to put what?
usually we represent vectors as a column, not a row.
Yeah.
That's the notation. You are representing it as a row, right? X.
Yeah, I guess X should have been a column.
Yeah, it
Is that
should
what
be
you're saying?
column, yeah.
Yeah, that makes sense.
If that's the, you can write as a row, but the norm is a column.
I agree. I should have written that transposed.
So at the end of the day, they do a little bit better than EWC on these tasks.
Yeah.
That's the.
But what's
But this is
interesting is not that's better, it's that it's a different approach and it's kind of the same.
Yeah, so
That's what I thought was,
maybe what Sujata was saying
Yeah,
is the
and
same, but that's
I'm not
actually
sure it's that
different.
different, actually.
Yeah.
it's very different.
Yeah, so so it would be really exciting if this was a completely different method, because then you could do both together and might get even better results. But my guess is if you try to do both together, it's not going to be dramatic.
So what we're asking.
I think they're actually more similar than it seems at first.
I think you're right, but we were asking yesterday is we combine these before sparse ones. Because the
Well,
premise
sparsity
here-
already gives you these properties.
Yeah.
You don't have to do all these context-based changes.
But
So,
could you
it's
combine and get like an even better?
But
But it'd be hard to
I
do
don't
these
know.
rotations without going from sparse to dense.
Yeah, that's
It's gonna be kind of hard.
You know, I don't think you would gain much. I mean, the Sparse seems almost like a perfect solution to this problem. But I think about it.
Does sparsity give us the this idea of like context collapse though? It seems like sparsity has this orthogonality. That for example, if the tasks that we're training on are actually like T1 and T2 are identical, we're still going to have these like sparse representations that are in totally different
T1 and
spaces.
T2 are identical.
Yeah, like instead of giving 0 degrees and 2 degrees, I just gave 0 degrees and 0 degrees. So it's actually the same exact input distribution. I told it that it needs to choose a different context matrix for task 2.
Why would I do that?
That's just the way they've set it up. Yeah.
I don't get it. You're saying we have this difference and now we're gonna ignore the difference. I'm missing it.
If you were fooling with this network and trying to see what it did when you have 2 different tasks, they're actually the same task.
You tell it, it's just really just one task and you tell it, I have 2 tasks.
Yes.
And now you're setting up 2 of these matrices.
Yes.
Okay.
I would want an adaptive solution to be able to have these contexts collapse on one another so that it's actually learned the fact that those tasks are the same. And I'm trying to figure out whether SDRs would give you that property or not. I think that.
Well, I don't think with SCRs we would do explicit context anyway.
Yeah, but
So-
the answer
So
is
that's the
Yeah,
question, like,
yeah.
why you're sort of artificially forcing it apart and then say, hey, does it come back together?
Yeah.
the SDRs force them apart already, isn't?
Yeah.
They're
And if they're similar, they'll match.
I see. So,
I mean,
yeah.
exactly how to use SDRs to do continuous learning in this kind of a machine learning context is still unclear to me. I can more clearly talk about what happens in the temporal memory at this point. But
I can visualize in the temporal memory as well, and you can ask yourself what happens. We did a lot of this stuff like, oh, you have 2 different melodies and then they get really similar and you stop hearing one or no, the other one is we have 2 different melodies, but then later you realize that they're the same.
Yeah, so this is when the same columns are winning in that case, right? So you just are actually learning the same SDRs.
Yeah.
No. That's hard to remember.
Well, there are several situations, like suppose you've learned a bunch of melodies, now you're learning a new set of melodies. Those new set would not interfere with the old set at all.
Right.
And you would get perfect performance.
But that's
in
not
all
the
of them.
collapse one we're looking at.
That's not the collapse one, but this problem would never occur in a temporal memory. You'd get like perfect flat performance.
Because different inputs.
Because different inputs
orthogonal
and-
spaces already.
Exactly, and the temporal memory is really good at that. The second aspect of continuous memory is maybe you learn a few melodies, but then one of these melodies changes. It's no longer that. It's easier to think about in terms of some real world stream that now, in some cases, some of them change. But what happened with the temporal memories, just those would get altered. The other stuff would not get affected. So again, no catastrophic forgetting, and the learning is contextual to the stuff that actually changed. You don't need context matrices, you don't need anything, it just does it automatically. And if you have context drift, similarly, it's gonna automatically
To me,
learn that drift.
the
and
concept-
old stuff will get forgotten.
We lost all our black pens in here. I was thinking of the collapse reminded me of like we have two sequences, A, B, C, and you have D, E, F. And there are two separate sequences, but then later on you realize that D, E, F is actually a continuation of A, B, C. So if I learn this, the D, E, F here is different than the D, E, F here. This is, in some sense you want that to be different. You say, hey, this D, E, F is not the same as this D, E, F, but then maybe it was, and so the question is, you collapse, does this one become, like that?
Yeah, that is context learning as well, right?
There was a lot of issues like that where we had to deal with at the time. Anyway, this is not about temple memory, it's about yeah. So the reason you brought it up, you said, I don't know if I have context collapse. And I guess questioning, is that really what you want in a real world system?
I think you've answered my question that you wouldn't need context collapse because already when the same inputs are coming in, if task 1 and task 2 are the same, then it's already going to be active in the same columns.
Yeah.
Where the SCR is going to be.
SCR,
Yeah, the SCR is within the same space.
Yeah. Well, it's this issue of that, like someone just said, how do you pick these C's is the big issue, right? That's the big trick to this whole thing.
You talk about analogies, and I was thinking that one way to think about it in terms of context is, let's say I want to explain you something, and I just say, oh, you just get A and mix with B, and that's it. And you could think of, I just get the context of A and get the context of B and mix them together, and then I have this new context. And I can start to think about this new task just using this new context. It's like a merge of A to B. So I'm using this analogy that it looks like that, so I have a starting point to learn this new task, just by merging existing context.
Because I see, yeah. It's,
Just thinking out loud.
I know context is low dimensional, so there's some value to being able to find like overlapping sections of context.
So you just like merge a few contexts and then you have like a starting point for a third task, So that would be somehow like knowledge. Right?
Because if you think of the context as an address into the parameter space, we say we want a context where we have like half of the address is still the same as this other task. So we're going to reuse those parameters, and the half the address is some new area that we need to learn.
Exactly.
So it's sort of like an attentional mechanism, right?
But how do you decide which one is large?
Yeah, I'm thinking of when you explain something to someone and then you use an island and you just say, oh, just combine A with B and C, and the person already knows A, B, and C, and you can just relate to something you already know. So that would be kind of
to automatically figure out the context. That's not in this paper, right? But so maybe there's heuristics that are used, like the distribution feels like it's in this totally new area that we haven't seen before, but part of the distribution is very similar. So we say, oh, let's take part of this context and part of this context. But how exactly that happens is like, I don't know, it's metacognition.
There must be like smarter ways of choosing. I mean, that's what we discussed, right? Smarter ways of choosing the initial context.
Yeah. I mean, another possibility is you just try all the contexts and you see, which one is doing the best job of doing prediction, and then you just choose the ones that are doing a good job. Like that's a possibility.
Yeah. Try a little bit.
Yeah.
Search in the space of context.
Yeah.
That's why we need more hyperparameter searches.
That's definitely not less computational.
Yeah.
That's all I had on this.
Okay. This is a cool paper. It's very interesting. In this kind of regime, I think it's a very clean way of thinking about it, a very clean way of looking at it. Whether it translates to realistic continuous learning or not, it's unclear. Okay, any other topics?
Matt, let us know when you're done streaming.
Okay, I'm gonna turn off the stream right now. Thanks everybody for watching.
Okay.